Today we will learn about the Riemann curvature tensor. Curvature is one of the most intuitive but also fundamental notions in geometry, especially in Riemannian geometry. There are different notions of curvature. The Riemann curvature tensor is one of them, named after the 19th century mathematician Bernard Riemann. Okay, so let's start with the simplest kind of notion of curvature. Think about curves in a plane, right? Just a straight line or one-dimensional curve kind of uh, drawn on a piece of paper in a plane. So what is curvature of these plane curves? Think about R2, say that's our ambient space. Think about the straight line drawn there. This straight line is straight, it's flat, it's not curved, so the curvature should be zero. Think about another curve, but now it is curved, right? It's not straight anymore, so the curvature at each point should probably be a non-zero thing. Okay, how can we define this notion of curvature rigorously? So one good way to think about it is by thinking about the circles in a plane. So for instance, think about a small circle with radius 1 over 2 and another circle slightly larger, let's say with radius 1, and another circle, let's say much larger. Here we see just a piece of this circle. This is a very large circle, let's say. Let's say the radius is 100. We can have another one which is much, much, much larger. So let's say the radius is 1,000 or a billion or whatever. And as the radius gets larger and larger, as you can see, a piece of circle is getting closer and closer to being a straight line. So in some sense, when we take limit, when the radius goes to infinity, we get the straight line, which is like straight, flat, not curved. That kind of tells us that curvature, when the radius is larger, the curvature should be smaller. So one way to quantify that is to define curvature to be 1 over radius. So if radius is 1 over 2, curvature would be 2. If the radius is 100, curvature would be 1 over 100. Kind of the straight line can be understood as the case where the radius goes to infinity. So the curvature should be 0, kind of like 1 over infinity type of thing, right? Now, if we look at these curved in plane, the other thing we have in R2, we can define the notion of curvature at each point. It's kind of like at each point finding a circle which is tangent to the curve at that point, right? And loosely speaking, it's like inscribed there in the sense that they have the same curvature, right? Locally, the circle is very, very, very close to the curve. I'm not making this very rigorous, but loosely speaking, you can find a circle there to approximate your curve there. And then the curvature of your curve at that point would be 1 over radius of that circle. So this is kind of an extrinsic notion of curvature. Here we're thinking about curves being inside R2. R2 is called the ambient space here, the larger space where your curves live inside that space. There is a different notion of curvature. There's another notion of curvature, which is more intrinsic. It's when you think about a manifold by itself, it's not embedded inside some larger space. So it's kind of like thinking about this straight line or thinking about the curve outside of this larger space. Let's say let's say you are living on that curve. Let's say you're not even aware of R2. The whole world for you is that one-dimensional thing. You don't even know this line is inside a two-dimensional space. Let's say we are points living inside this kind of curve. Can we differentiate these two curves? If you're in a straight line, would we understand it's a straight? And if we are in a curved line, if we are living inside that curve, can we understand this is really curved without being aware of two-dimensional space? Right. So I like you to think about this. The honest answer here in the one-dimensional setup is no. If we are like a point living inside that curve or living in one of these circles, well, we might go around once and see we are coming back to the same point. But if we think about it just locally, if you are just a point, if we go a little bit to left or right, If we are not aware of this R2, if the whole world for us is this one-dimensional thing, in fact, we would not understand that this circle is curved. We could not differentiate between that and a straight line. I leave this to you to think about it, to see if it's kind of intuitive to you or if you accept it or not. Okay, you can share what you think about this. Now, we can think about the same question in higher dimensions. Like you can think about, say, a surface being inside R3. This is actually first was kind of more rigorously was studied by Gauss. This is related to something called Gaussian curvature or essentially scalar curvature. Think about three-dimensional space. Think about two-dimensional surfaces being embedded there. We can think about a plane there, flat plane, just straight, kind of flat plane there. We can think about the sphere, two-dimensional sphere being there. We can think about the two-dimensional cylinder there. It's just empty inside. It's just two-dimensional. Or let's say we can think about the saddle, the kind of two-dimensional object which resembles saddle. So again, we can think about these things being inside R3, kind of in the extrinsic sense. So the plane is flat, right? I think that's pretty clear. And what about the other surfaces? Okay, if we are a person inside R3, we can see all the other three objects are somehow curved, right? They don't look flat to us. But what if we are points again, living inside or living on these two-dimensional objects without any understanding of the three-dimensional world? Would we recognize that? What if we are a point on the surface of this two sphere and there is no way we can understand about this three-dimensional world? Would we understand the sphere is curved? What about the cylinder? Or what about the saddle? If we are a point living on the cylinder, can we understand kind of the cylinder is curved, especially locally? Let's say you're not really going around one. So if you just look at the kind of neighborhood of one point on the two-dimensional object, would you recognize this is curved? This is the essential question which was studied by Gauss. And Gauss gave kind of positive answer in the sense of Gaussian curvature. So in the case of sphere and in the case of saddle, we would recognize that. So there is a type of curvature called Gaussian curvature, and it is kind of intrinsic. It is intrinsic and it is non-zero. So if you live on this two-dimensional object, you really understand that, say, sphere is not really flat. You would not recognize that on cylinder, though. The Gaussian curvature of the cylinder is still zero. So I'm not really going, we will discuss this later, not now, but just a way, a hint, a clue for you to think about it is that if you have a flat plane, if you look at a triangle on that, the sum of the angles would be pi, right? The angle of A, B, C, they sum up to pi, 180 degrees, right? What about sphere? What about saddle? And what about cylinder? This is kind of quite related to the notion of curvature. If you think about the two-dimensional sphere, if you think about a triangle on this two sphere, let's say we start from A, along a straight line, which would be a geodesic, kind of continue until we get to some point, say B, go in another direction on a straight line, get to C, from using the straight line, go from C to A, we get a triangle on this space. And the point is that you can try this with different triangles. We see two of them here. You would see here the angle of A plus B plus C would be larger than pi. It is not equal to pi. So that's something, a point which lives on that sphere can do. You can draw a very small triangle and you see the angles would sum up to something larger than pi. You can do the same thing on a saddle. If you draw, I'm drawing a large triangle, but even if you draw a very small triangle, you would kind of see that, although it would be harder. But you would see here the sum of the angles A plus B plus C would be less than pi. You can kind of see that in this schematic drawing. And that is related to how these two surfaces are curved. The sum of the angles is kind of related to the curvature of this surface, kind of independent of this being embedded inside R3. But the point is that if you do that on a cylinder, it still would be pi. You can see that by just drawing these on like a piece of paper, and then you can make that thing into a cylinder, right? Your triangle would still be a triangle, and the angles wouldn't change when you make the plane into a cylinder. It still would be pi. That's like a sign about why this notion of curvature would be zero for this flat plane becoming cylinder. Still, there is other notion of curvature for this cylinder, which is non-zero, the more extrinsic one. But today, actually, we are going to discuss not about the Gauss curvature. That was just an introduction to make you think about it. Today, we are going to discuss about something called Riemann curvature tensor, essentially defined by Riemann and later by Christoffel, Ricci, and others. This is not a number. In fact, as we go to higher dimensions, it's very hard to describe the curvature by just a number. So suppose we have a higher dimensional manifold, the dimension m can be anything, with a Riemannian metric and the associated Levi-Civita connection. Remember that whenever we have a Riemannian metric, there's a unique connection which is compatible with that metric and it's symmetric, called the Levi-Civita connection. Okay. The curvature, Riemann curvature tensor, sometimes in some books denoted by R, sometimes denoted by Rm, sometimes denoted by Riem, essentially coming from Riemann, name of Riemann. It's not a number, but it's like a map where the inputs are three vector fields on the manifold and the output is another vector field. So it's much more complicated object. It is not a number, it's like a function. The curvature itself is here a function. It takes three vector fields, so each curly x of m denotes the set of vector fields on your manifold M. This function, the input are three vector fields, and the output is another vector field. How is it defined? So let's denote this with Rm. So the input are three vector fields. Let's denote these three vector fields by x, y, z. Okay, what is the definition? Take the covariant derivative of z in direction of y, then take the covariant derivative of this object in the direction of x, minus. Take the covariant derivative of z in direction of x, and then take the kind of second derivative in direction of y, minus the derivative of z in direction of Lie bracket of x and y. Okay, this might kind of look complicated. Why do we define kind of curvature this way? What type of curvature is this? What is it measuring, right? So in order to understand this, let's say this is schematically our manifold. Let's pick x, let's say at least in a small open neighborhood, to be the vector field given by partial xi, right? Remember, we could pick an orthonormal kind of basis at one point, being image of E1 up to En. So let's say x is the kind of the constant vector field partial xi, y is the constant vector field partial xj. And their Lie bracket would be 0. So if we plug in partial xi and partial xj instead of x and y and some other z, we would get the covariant derivative of x in direction of xj, derivative of that, second derivative in direction xi, minus first derivative in direction xi and then derivative in direction xj. And because Lie bracket of partial xi, partial xj vanishes, that's it. Okay, so in both terms, we are taking kind of second type derivative, but in once we take first with direction xj and then in direction xi, and then in direction xi first and then direction xj. So we remember from calculus, usually it doesn't, the order we take derivatives don't matter in Euclidean spaces. In fact, in general, that's not true. It can be that here, this kind of quantity is not zero. So essentially, curvature measures how much taking derivative in one direction and the other direction would be different from taking derivative first, say, in the other direction, and then in the direction we took earlier. So it kind of curvature measures how much this kind of mixed derivatives do not commute. So if you have a curved space, it's not necessarily true anymore that the second derivatives would commute. Okay, so the Riemann curvature is a tensor. What does it mean? Essentially, the meaning of it being tensor is the following, is that it is linear in each component. It's not just linear with respect to addition and multiplication by a constant, it's linear even with respect to multiplication by a function. In the sense that if I multiply the vector field x by a function f, that would come out of the tensor. So it would be the Riemann of fxyz would be equal to f times Riemann curvature tensor of xyz. That's true for all components. It essentially means this is a tensor, and it also equivalently means it only depends on the values of these three vector fields x, y, z at a given point. The curvature at each point, when you want to compute that for x, y, z, only depends on the vectors x, y, and z at that given point, not the behavior of these vector fields on neighboring regions. Okay. There are a few properties of the Riemann curvature tensor which are quite essential, and those are related to the symmetries of the Riemann curvature tensor. Okay, I'm going to mention a few of them here. We would see some other symmetries later. They're kind of essential in proving anything about the Riemann curvature tensor. Okay, let's just denote for simplicity this tensor by R. It takes three vector fields x, y, z. What would happen if I just change the place of x and y? It's easy to see. You just get a minus sign. Okay, so Rxy equals to minus Ryxz. Now, what is Rxyz plus R of yzx? Let's start to kind of shift them by 1. And then let's try to shift them once more to get R of zxy. Well, they sum up to 0. This is also quite important. Another thing we can do is that let's look at Rxyz. Let's say we have a new vector field, a fourth vector field denoted by W. What would be, so Rxyz is a vector field. Let's look at the inner product of this vector field with W at every point, right? This would be a real number. Now, let's say we change the place of W and Z, okay? And then look at the inner product. What would happen then? We just get another minus sign. Okay, and finally, let's say we are looking at R of x, y, z, and again, we look at the inner product of this vector with W, right? This would be a real number. Okay, now let's look at the Riemann curvature tensor of R of z, w, and x, the inner product with y. It's also a good exercise to show. Again, you would get just a minus sign. Kind of, I leave proving this to you. This would be a good exercise, but it's actually kind of nice. A good hint or clue how to prove this can be found in this picture illustration in the book Morse Theory by Milner. Okay, it's a good place to stop.